To better understand the chemistry of acids and bases, we need to understand that they are typically involved in an equilibrium. So when we look at ammonia acting as a base, we can see that ammonia is grabbing an H plus from water to make ammonium and hydroxide. And what we need to do now is consider the fact that the reverse reaction is also occurring. So ammonium is reacting with hydroxide to remake ammonia and water. So to better understand this relationship, we write the basic reaction of ammonia as an equilibrium. So we use the double-headed arrow. Once we understand ammonia and other bases are actually involved in an equilibrium, we can use the ideas of equilibrium that we learned in the previous chapter. In this case, we can understand that the relative ratios of the products and reactants can be expressed in an equilibrium expression. So here, the same basic ideas for creating an equilibrium expression for a given reaction. It is products divided by reactants. And in this case, water is not included in the equilibrium expression because it is a liquid. So we only include the aqueous species. So here are products, ammonium and hydroxide, divided by the reactant ammonia, and water is left out. And also what we have is this equilibrium expression is equal to an equilibrium constant, in this case 1.8 times 10 to the minus fifth. So this is a specific type of equilibrium called a KB, and it is defined as a base ionization constant, and we know we're talking about a KB expression when hydroxide is produced. So where we're going to go from here is, in order to understand the acidic and basic properties of, in this case, ammonium and ammonia, we need to understand how this equilibrium comes into play, and that's what we're leading to in this chapter. So the same basic idea applies to acids as well. When we see hydrofluoric acid reacting with water to produce F- and hydronium, we need to consider the fact that the reverse reaction is also occurring. So even when we have an acid, we now need to understand that there's an equilibrium involved. So it's still products divided by reactants, so F- times hydronium divided by HF. Once again, water does not show up in our equilibrium expression, and our equilibrium expression is equal to some equilibrium constant. In this case, it is called a Ka, or an acid ionization constant, and we know this because hydronium is being produced. So just like other equilibrium constants, these equilibrium constants Ka and Kb are unitless, but we can assume that the units are in molarities, and that's what we're going to be using going forward. These equilibrium expressions are going to be especially important when we start to work with weak acids and weak bases. So here we know that HF is a weak acid because our equilibrium constant is a very small number, so 6.6 times 10 to the minus fourth. That means the relative amount of F- and H3O plus to HF is very small. So if we put HF into solution, only a very small of it will dissociate into H3O plus. So to be able to understand how acidic a solution of HF is, we need to know the equilibrium constant, and then we also need to utilize the equilibrium expression. So typically when we talk about Ka and Kb values, we are discussing weak acids and weak bases. So to be able to understand the properties of weak acids and weak bases, we need to know their equilibrium constants. So with strong acids and strong bases, they are technically still involved in the equilibrium, but the K value is so large that we can discount it. So if we look at a strong acid like HCl or a strong base like NaOH, the K values are extremely large, and this means that the equilibrium is pushed virtually all the way to the right. So we don't need to involve an equilibrium expression. We say if I put in 1 mole of HCl, that's going to disassociate to make 1 mole of hydronium. So we don't need the calculations. So the KLEP values, because they're so large, we can just assume the equilibrium is all the way to the right.